warm welcome to you all, and hope you had a great weekend. The kind of mails which I send during the weekend, I normally often update the files also in the morning. So you will probably see that the Jupyter notebook, which I sent yesterday, has been slightly updated with some corrections of typos, etc., etc. Now, what we are going to do today is actually something which will stay with us for the rest of the semester. And in a certain sense, you can also consider that as one of the main cornerstones of Project One. So what we are going to deal with today is actually to look at the family of gradient descent methods. And in the slides, you will find lots of examples which you can use when you write the code, your own codes for Project One, or you can just use them as inspiration. Now, what we are going to do first is to remind ourselves quickly what we did last week. And then we are going to move into gradient descent with momentum, which to me is a kind of not the best name. I like to call it memory, because we keep track of previous iterations. And we are going then thereafter to introduce stochastic gradient descent. Now, you will probably feel during Project One that stochastic gradient descent, which is less accurate than the standard gradient descent, if you can do that, is perhaps a kind of overkill for Project One. But that's because we are dealing with methods like ordinary least squares and ridge. But when you come to neural networks and deep learning methods, this is the method of choice. So we are going to introduce you to that. And then we have these popular methods, which are called the second order momentum methods, like adaptive gradient, root mean square propagation, etc., etc. And these are methods which we will discuss and which we need to implement in Project One. But let's remind ourselves quickly about what we did during the lecture last week and bring up the results from last week. And let's take a quick look. So today, this is just a repeat of the topic. But what we essentially did last week was to make a Taylor expansion of the cost function around the optimal values of the parameters theta. With that Taylor expansion and keeping terms to second order, we could derive Newton's method. That was essentially the kind of mathematics which we used last week. So what we ended up with is an equation for the parameters, which are then being updated iteratively. So we start with a guess of theta 0, so n equal to 0. And this contains this matrix, which we call the Hessian matrix. And this depends on theta n. So this is the second derivative. So we have to invert that matrix. And this is multiplied with the gradient of the cost function with respect to these parameters theta. So this is the gradient of the cost function at the value theta of n. So the basic recipe here, which we discussed last time, is that we start with a specific guess, and then we keep iterating till the gradients are 0, or theta n plus 1 minus theta n is smaller than a given number which we have set. So typically what you would do then is to start with a guess. This is just nothing but Newton's method for the roots of the gradient. So we will start with a guess, theta 0, which means that if we now take a very simple function in one dimension, so we have a theta optimal here, and our function is just a convex function, and then we have some theta 0. And then we would start calculating the gradients, and ideally, we should then have chosen this starting point so that after a given number of iterations, we get down here. And then we would stop iterating when this theta of n plus 1 minus theta of n is smaller or equal to a number which we set, and this could be 10 to the minus 5 or smaller. Another possibility is to calculate the gradients and just see that the gradient is getting close to 0. This is normally less efficient than calculating this specific norm. So remember now that theta is a vector. Okay? So this is essentially what we derived last week. And we have been applying this to these methods like ordinary least squares, ridge regression, and lasso regression. So let me quickly remind you of some of these expressions here. So the h of n, which is called the Hessian matrix, is actually the second derivative of this cost function evaluated at this value theta n. So this is d of theta squared. I'm just writing it like that. So this is evaluated theta equal to theta n. This is actually an extremely time-consuming process, and sometimes it's almost impossible to calculate these second derivatives. So this is going to be a matrix which then contains all the possible second derivatives. And it's pretty common to replace this one with a parameter which we call for eta, and it has a n here. You can keep it constant, or you can set it up in an iterative way. The simplest possible approach is the one which we discussed last time. And then we simply had what's called the plane gradient descent, where we have an update rule of minus this eta, and eta is just a constant multiplied with a gradient. This is normally called the plane or simple gradient descent, or just gradient descent. So by choosing that parameter, which we'll call the learning rate, so this is simple plane gradient descent, and I'm going to just write this as GD. So this parameter which we have introduced here has a name, and it's called the learning rate. Now, what this means in practice is that we, in many, many cases, especially when we train neural networks, it's cheaper from a computational point of view to calculate for a certain number of these parameters eta, and then simply take the one which gives the best mean squared error. Because to evaluate the second derivatives is, as you will soon see pretty soon, is extremely expensive. And also we have to invert a matrix every iteration. And we don't want to do that. So if you have 1,000 parameters theta and you do 1,000 iterations, you have to evaluate the inverse of that matrix 10 to the 6 times, 1,000 times 1,000. And you don't want to do that. And then it's much cheaper to actually run the calculations with many values of eta, and then find the one in the landscape of eta values, which gives you the best result. And when you peep into libraries like scikit-learn, PyTorch, and TensorFlow, you will find functions like grid search, which actually allows you to find the optimal value in a grid of values for eta and also other hyperparameters. So it sounds like a little bit like cheating, but for the ordinary least squares, the methods we have looked at, we can actually do better. In some cases, we have analytical answers. So let us quickly remind ourselves about the gradients, which we are going to calculate, because that has also consequences for what we are going to do. So let me quickly remind you of the gradients, which we get when we use the different methods. So ordinary least squares, then we have a gradient where I just write it like C of the gradient with respect to theta. And that is given by 2 divided by n. And then I can write this out as x transpose. This is the design matrix times x of theta minus x transpose times y. So quick reminder, X is a matrix of dimensionality, the number of data points times the features. Theta is a vector of length P, and Y is a vector of length N. Then we can do ridge. And in ridge, what we have then is the following derivative. And these are all equations which you will have to plug in into the project. So in that specific case, we have the same as we have in ordinary least squares, minus xt of y. But then we get an addition, which is a parameter lambda, multiplied with 2, multiplied with theta. So remember now that theta is a vector. So that's the gradients which we need to implement in project 1. And what you're going to see then is that this allows us to rather quickly change between ridge and ordinary squares, because the bulk of the gradient comes from the mean squared error. So when you have coded the first term, the ordinary squares, the only thing you need to add when you do ridge regression is to add just 2 times lambda times theta, and that introduces a new term. So this is essentially what we will practice this week in the exercises. And you did some of it last week, but then you just inverted a matrix. And then finally, we have lasso regression. And 2 divided by n of x transpose times x. So we have the same piece from the ordinary least squares, mean squared error. And then we have plus, and then we have lambda times the sine of theta, because we are calculating the derivative of an absolute value. And this is an equation which we have to solve numerically. So in project 1, for the exercise or part E, you will actually have to implement this numerically. And that's one of the additional, bits of pieces we won't give you in the lectures, but which you will have to figure out how to do yourself in the project. We're going to give you hints during the exercises, obviously, the exercise sessions. So this is essentially what we did last week. One of the things which we also did last week, and that was to expand this the cost function in terms of the gradients. So what we have now is that the optimal value, theta of n plus 1, is now given by theta of n minus, and now we're going to put this as a constant of g. This is the gradient. So I'm just going to write this in terms of a shorthand, and you will see that many times in the lecture notes here, that I'm going to use the symbol g for the gradient. Now, I'm just going to do a kind of a small intermediate step here in order to find the optimal eta by looking at a Taylor expansion around that specific value for theta. So what I'm going to do now is to Taylor expand again. Expand around. And then I'm going to Taylor expand around this quantity here. So I'm assuming that I have reached convergence, so that theta of n plus 1 is the optimal value. And now I'm just setting up an expression where I keep terms to second order. And then we keep, as we did previously, and keep only terms to the second order, which is the second derivatives, to second derivative terms. So when I do that Taylor expansion, I will obviously have an expansion in terms of this value theta of n minus eta times g. And let's see what that looks like when we set up the expression. Any questions so far? So this is just a small addition to what we did last week. And I'm going to write this in a more compact form here. So what we are going to get then is a C of theta, and this is the optimal value, which we normally have labeled with a C of theta hat. So suppose it has converged. This is going to be equal to C of theta of n. This is just a constant. Then I'm going to have the gradient, gt, because now this is a gradient, and then which is the derivative. So this is the first derivative. And then I have to multiply it with a term I'm making the Taylor expansion around. So I have minus eta, g of n. And then if I now stop at the second derivative, I would have a half. And then I have theta of n minus this term eta, and then g of n. So this is a matrix vector product. So we have this h, then the second derivative, and I write this as a function of n here. So that depends on theta n. And finally, this is multiplied by theta of n minus eta of g of n, like that. Now I want to find optimal. So I'm assuming that I've reached the optimal value. And I'm asking myself, what is the optimal eta value? So if you have this expression, if I want to know I'm asking myself, can I use this to find a value for eta? How would you guys proceed if I give you this expression? You want to find the optimal eta value. So which function would you drive to 0? And how? Any good suggestions? So what if I take the derivative? Yeah, you have it. Yeah, the derivative with respect to eta. So what I'm doing now is I simply take this expression and I want to find that one with respect to eta. And I want to drive that to 0. Now, when you do that, you see that you will get a term here, which has minus g times its transpose. It's only this term which depends on eta. This does not depend on eta. This does not. This does not depend on eta. So it's only this term, and that term which comes into play. And there we have eta squared. Take the derivative, get 2 divided by 2. That means that when we do that, this becomes, if we do this, we get a nice expression for eta. So we're going to get minus g transpose for iteration n, g for iteration n, plus this eta, and then we have g transpose of n of h of n of g of n. And we want that to be 0. And if I do that, I can actually calculate a value which is given by this inner product divided by us calculating the product of the transposed vector times the matrix which contains the second derivatives multiplied with this vector again. Now, has anyone, yeah? Say it again. G is the gradient. So it's just a shorthand for the gradient here, because instead of me, and you will see that in the equations which are coming, that I'm going to replace the gradient, as I did here, with just this G here. Now, this equation which you have is linked with a method for finding the optimal value of eta. Now, you see quickly now that what you have is an inner product of a vector, which requires some floating point operations, but it requires that we know the matrix H, okay? And we don't want to use that because the matrix H is something which is difficult to calculate. This method has actually a name in the literature, because what we would have now is an eta which changes for every iteration. Has any one of you encountered that method in optimization theory? It's one of the more popular methods when you're optimizing a function. It has descent in the name, but it has another adjective in front of descent. Anyone seen that before? Have you guys heard about steepest descent? This is steepest descent. This is for us, if you now think of a neural network. In a neural network, that matrix H can have dimension 1,000,000 times 1,000,000, or even higher. So this method is for us useless, unless the matrix H is pretty small and we have few features. Okay? So one of the reasons why I'm bringing up this is that I'm going to motivate what is coming, which is stochastic gradient descent and other methods, because the dimensionality can quickly become huge, especially when we implement directly a gradient descent method. Now, if I assume now that I can make a small assumption now, and that this G is an eigenvector of H. So suppose now that H of n, this is just a very, very rare case, but suppose now that this is the case. If that is the case, then what you will see is that eta of n is going to be equal, and now I'm going to skip the superscript n. So this would just be given by G transpose times lambda times G, and that is 1 over lambda. That's interesting. Now, it's interesting because there is actually a theorem. If you can calculate, or actually a mathematical statement, which we are not going to prove here, but which we are simply going to state, and that is that there is a requirement on this lambda. So the eta requirement and that eta is that eta should be smaller than 2 times a lambda max, where this is the largest eigenvalue of the Hessian matrix. Now, this Hessian matrix for ordinary least squares is nothing but this matrix X transpose times X. So for ordinary least squares, we can actually calculate this quantity. However, you see quickly that if we want to use that as a measure, we actually have to calculate the second derivatives. And the whole reason for everything we're going to do today is actually to avoid to calculate the second derivatives, because that's going to be extremely difficult when you have tons of parameters. Okay? So let's now go back a little bit. So this is just, if you look back in the codes, the first codes which we had last week, we actually used this criterion to set the learning rate. And we saw also that if we broke that criterion, we got results which were wrong. So if you look at this criterion, the typical situation you are going to encounter when you're going to optimize, and suppose now we have a gentle convex function. So this is the theta optimal, and we have theta here. You would typically start with some theta of 0. And now depending on your learning rate, you may converge in different ways. So this would be the gradients. So the first value, and then you have the next value. So this is multiplied with eta times the gradient. This should be a theta. And this goes all the way down here. And ideally, after some iterations, we should reach this point here, the optimal value. And this is the point where delta theta of C is equal to 0. Then we have found what we might call an ideal value for eta. If we make it too small, what could happen then is that we barely move. So then we could stop here, there, and after a given number of iterations, we are here. So in that case, we have eta too small. Because typically, we will set a number of iterations. We cannot iterate ad infinitum. And the simple reason for that is that it's going to cost you tons of CPU cycles. So that means that we have to set a kind of limit on the number of iterations. And then if we are unlucky and choose eta to be too small, we may actually stop far away from the minimum. Now, if eta is too large, what could happen then is that we start here and then we jump here. So in this specific case, eta is too large. And then I may jump here, and then it just jumps away. And it never reaches a convergence, and you get typically not a number. And we saw examples of that last week. So we have a criterion on the learning rate. However, that implies that you can calculate the second derivative of the cost function. And this is the whole thing we want to avoid. So everything we do in machine learning is going to rotate around us implementing this algorithm which you see here, this one, in one way or the other one, where we are going to find ways to update the learning rate in ad hoc ways or more insightful ways. And that is what these methods are about. So it sounds disappointing, but this is roughly what we have to face when we are dealing with multivariable functions. These can be non-convex functions, can be convex, it can be strongly convex. We don't know before we have actually started to look at the function. Any questions so far? Okay, we are going to break a little bit now because I wanted to ask you guys some questions. And we are going to look back at the equations here. So just keep in mind this equation here, which is the one we have to code. And we are going to switch a little bit. So just to break the monotony, let me see if I can find it. Here we are. You're probably familiar with menti.com. And you can actually, so menti.com. So if you bring up your cell phones, can everybody see the number up there? It's 46398306. So if you look at the equations we have for ordinary least squares, these are actually nice equations from an optimization point of view. So if you look at that equation with x transpose times x, is x independent of theta or not? Let's see what the popular voice says here, the voice of the people. So if you look back at what you've been programming, no dependence on this, independent of theta. So it's actually in the text. Is x independent of theta? Is x a function of theta? Yeah, that's what it means. Okay, we can just let this go a little bit. Now, if you, so the answer is yes. So x does not depend on theta. That's the nice thing with these linear regression methods. Just keep that in mind, that's important. Because when you come to neural networks, this is no longer the case. Because then, when we are calculating derivatives, gradients, we are going to back propagate, and then we will have a dependence on the parameters for the derivatives. And then this nice, gentle situation here is not going to be there anymore. Now, if X is independent of theta, so thanks for everybody for responding. Let's go to the next question then. Because this has an importance when we are looking at the numerical results or the numerical implementations. So this is more, how to say, a question, a free question. And let's see what people mean here. So when you're setting up your code, so think of this in terms of the numerics you're going to implement. And look back at the equations which you're going to implement. Say again. I have to get closer because I mean, only for what we are doing now. So this is essentially project one. So you can actually simplify the calculations and just take a look back at the equations you have. So you have to calculate this matrix and you have to calculate this guy. So what kind of, yeah, we can calculate, yes. Yeah, go ahead, guys. Let me see what people think. So you can calculate analytically, absolutely. There is the gradient descent you're going to implement in project one is essentially going to be of importance for the lasso regression, because that's where we don't have an analytical expression. So if you are so lucky to have an analytical expression, use it. There's no point in mounting X and Y constants. Exactly. Love this. Yeah, you can normalize the X values. That's also possible. But we are thinking of numerical simplifications. Yeah, take this. Yeah, you can also do that. These are all good suggestions. I actually love this menti.com because it's less intimidating than the teacher asking you in the classroom. I was always in the back and I never dared to answer. But this can be a little bit more welcoming. So let's see. So for you guys in the audience here, if you look at these answers, which one, if I'm telling you now, which one can save us cycles or floating point operations? Because that's, so when I'm thinking of the simplification, when you calculate the gradients, this is when we are implementing this numerically. So which one of these statements would you opt for? They're all relevant, but there is one which is actually one, two, or three here, which are more relevant than the other ones from a computational point of view. Any good ideas? So let me try to show you which one are the most relevant one. So actually, this one, X and Y, are constants. They don't depend on theta. When you look at the gradient of the descent method, you're updating theta. So that means that we can pre-calculate them. And that is a big saving. We're going to go back to that when we look at the equations on the whiteboard. So this one is important. Treat X and Y as constants. X and Y are constants. X transpose times Y will be constant across iterations. So if you go back to the equation here, you can see now that we could pre-calculate this before we start implementing gradient descent, and we could pre-calculate this one. So this is just a matrix, X transpose times X. X transpose times Y is a vector. So we could pre-calculate them, because else, if I'm doing 1,000 iterations and I'm doing 1,000 parameters, I'm going to calculate these guys here again and again and again. And that's a waste of CPU cycles. So if anything I can pre-calculate, do it. So that's why it's important to think about these things before we start coding. So if we then, yeah, that's also something I recommend. Thanks, ChatGPT. Yeah, that's a good thing. But let's actually, if you ask ChatGPT, try that, to write a gradient descent code. It won't do these efficiencies for you. I tried it yesterday, and it didn't. But I didn't give it many hints. I just said, set up a gradient descent code for ordinary least squares for me. And it did it the most inefficient way possible. Okay? But it's a useful tool. So let's, now the reason why we are bringing up this is simply because these are considerations which become very important when we are coding deep learning methods. So think of large language models, which we are not going to code here. They have trillions of parameters, trillions. And you don't want to be inefficient when you have trillions of parameters, okay? So if you now think of this matrix X transpose times X, I don't know how much you have seen of this before, but there is something we call floating point operations. And when you count floating point operations, we are very democratic, because then we say that addition, subtraction, multiplication, and division is just one floating point operation each. But normally addition and subtraction are cheaper than multiplication and division and square roots, etc., etc. But if you now, I don't know if you have done this before, but if you've done it, try to set up the number of floating point operations which are required for a matrix multiplication. And later we are going to look at that for a vector multiplication. So let's just see, what is your verdict? So any good suggestions for the number of operations which are required when you do a matrix multiplication of a matrix of dimension n times p? Yeah, p squared, p times p minus n times n. Yeah, that's pretty good. And now you see also why many of these methods favor a small number of features with respect to the data set. Normally, number of p, which is the number of features, is much, much smaller than the number of data you have, which means that the final matrix X transpose times X is a matrix of dimension p times p. But if this is a square matrix, if p is equal to n, then the last one is correct. It's n cubed. It's actually 2 times n cubed. But the one which is closest to the answer is actually p times p minus 1 times n. So if you want to write it down for that specific case, I'm just going to write it on the blackboard, but it's actually 2. Let me just put on some light here. Right? So the answer is actually 2 times p squared times n. So those of you online can't see it, but it's 2 times p squared times n. If this is a square matrix, n times n, this is n cubed. So you can quickly see now that if you have a matrix which is 1,000 times 1,000, this requires 1 million of floating point operations. So if I am, and now you start to see the expenses here, if I'm going back to the expression which you have here, if I do this multiplication every time, then I would do 1 million floating point operations again and again of something which I can pre-calculate. So that would be a horrible waste of CPU cycles. And if you have 1,000 iterations you're doing, you will be doing this 1,000 times. So that becomes quickly 1 billion of times doing matrix multiplications of a given set of floating point operations. So if you then go back to the final question, suppose now that I multiply this with a vector theta, and theta has dimension p. So remember now that X transpose, as we wrote in the slides, has dimension P times P. So, and the vector theta has length P. So any good suggestion for how many floating point? Yeah, X, exact. Yeah, 2P times N. Excellent. That's the answer. So this is the number of floating point operations which we would have to do if we don't do any thinking. And you see that putting X transpose times X, everything which is independent of theta, and to pre-calculate it is fundamental. Now, for the cases we are going to look in project 1, this is normally what we call vanilla cases, or if you want to be a little bit arrogant, baby cases, because they are really small dimensionalities and you run it quickly. But in principle, when you come to neural networks and so on, not thinking about the dimensionalities becomes crucial for us. So let's go back to the Jupyter Notebook. Thanks to everybody. I hope you didn't find this too boring. So let's go back to the Jupyter Notebook and try to look at the programs which we had last time. So last time we looked at a simple gradient example where we took the mean squared error. And we had only 2 parameters. So that means that the design matrix with 100 the values of X is just a 2 times 100 matrix. Actually 100 times 2, sorry. And this is the function which we can just write out in terms of the parameters theta. And we can also calculate the derivative. And you did that nicely in these weekly exercises. So these derivatives are now functions which we are going to plug in when we write the code. And our simple code then, which we discussed last week, is actually one. And as you can see here, there is no dependence in the second derivative on the parameters theta. So I can actually pre-calculate the Hessian matrix as well. And what I did in that example last week was simply to implement the simplest possible gradient descent, where I simply implement this recipe here. And then I had this exciting function, which we have looked at many times, 100 values. Y is equal to 4 times 3 plus X plus some random noise. This is my design matrix. Now I use the Hessian matrix and diagonalize it to find an estimate of the parameter eta. And here I print just linear regression. And when we run this code here, what you will see now is that the gradient descent, and I have no stopping criterion here. And I also mentioned last time that if I put this equal to 2, so that is above the criterion on eta. If I do that, what you will get is just rubbish, as you can see here. So the parameters, and if I make it even larger, if I put it to 2.5, you see there is no sign of convergence. And then the estimated values, if you remember that figure I showed you on the whiteboard, where the value could just go far away, this is an example on when you made your learning rate too big. So tuning the learning rate is one of the things which we will do unless we have the possibility to calculate the Hessian matrix and its eigenvalue. Now, the other thing which we did last time was simply to do the same for ridge. and then we set up the equations, and this is roughly what you will have to do in the exercises this week. So I'm just repeating that. And in that specific case, we have another equation for the eigenvalues, which is almost as simple as we had for ordinary least squares. And in that case, I'm just setting up the Hessian matrix in my case here. So this is my identity matrix. The Hessian is now simply the standard one, but now I have these parameters lambda. Now, in this specific case, I'm just running this for one value of lambda. And if I do that, exactly the same case as we had before, you can then see that the values, no, wait, that was not that code. It's this code. And then we should take a break. And you see that it's not that bad. When lambda is equal to 0, that's when I will have a perfect match. So after the break, when we have discussed a little bit about the limitations here, we are going to look at momentum-based gradient descent. And you will see that this is just a cheap trick, which allows us to get a faster convergence. So the way I want you to think before we take a break is that everything we are doing now, we are gearing that up towards deep learning methods, when you are going to have zillions of parameters to fit. So these cases here are useful because then we have analytical expressions we can compare against, and it gives us confidence that the code we have developed functions. That's also important. Any questions, guys? We'll take a small break. Is that okay with everybody? Okay, let's do that. So in the weekly slides, you will also find a short summary of this gradient descent methods. And the gradient descent, as you saw from that example, with a fixed learning rate is very quick and easy to implement, but it has many drawbacks. And the algorithm, if it is deterministic, if it converges, it will converge to local minimum. It's extremely sensitive to the initial conditions. And you saw that from the example before the break, that if I change the value of this theta 0, I could get something which converged quickly to the minimum, or it could take many steps, or it wouldn't converge at all. So it's extremely sensitive to the initial conditions. And then if you have large data sets, then it's actually very expensive to calculate the gradients. And when we come to deep learning methods like neural networks, the matrix which you have, this X, etc., is going to depend on the parameters, because we're going to backpropagate. And in the backpropagation, you will have variables which you will calculate the derivatives of, which will depend on the parameters. And then it becomes expensive to actually mount the full gradient. So what I'm aiming at is actually the introduction of something which is called stochastic gradient descent, which we are coming to a little bit later today. But what we are going to look at now is a very simple way by which we can increase the convergence of the standard gradient descent. And let me show you this method and how you can implement it. So this is called gradient descent with momentum. Now, this is something you can implement in many other methods, except methods like adaptive gradient, the root mean square propagation, and ADAM, which actually deal in one way or the other one with this kind of so-called momentum, which I like to call memory. So the example which we are going to see, which just follows here, are just two simple examples. And I hope you don't get offended if we have a fancy function like x squared and a derivative, which is also pretty known. We are just going to look at that function and just count the number of steps we need with the standard gradient descent and gradient descent with momentum. But let's go back to the whiteboard and take a quick look at the philosophy behind this momentum method and what we need to encode. So this is one of the other methods we have to look at in project one. So there's a plethora of methods when you look at all of these, and then you may ask yourself, which one should I use? Now, the common wisdom from experience is to use the method called ADAM, which is an adaptive gradient with momentum. And that's one of the more popular ways to update the learning rate. But let's take a look at the gradient descent with momentum before we then move over to stochastic gradient descent and other methods. So why do we call this momentum? I have to confess, I never liked the name. But let's go through the kind of approach which you will typically see in most textbooks. So GD with momentum. And you will see why I prefer to call it gradient descent with memory. So suppose now that you, as an example, so the roots of this equation comes actually from Newton's equation of motion. So let's look at that. Newton's equation of motion, or Newton's law. So you have an object with a specific mass, and we're looking at this in one dimension. So we have the second derivative, the acceleration. We have a friction term where we have a friction parameter. So this is normally some friction. And then this particle moves in some external field. And then we know that the force which acts on that is actually the gradient over potential, or the field. So this is going to be replaced later with a gradient we have seen in gradient descent. So this doesn't look like a method we can use for gradient optimization. So where's the connection? Now, the first thing we need to do is to discretize the derivatives. Discretize. And I guess most of you have actually seen the discretization to the second derivative. This is called a 3-point formula. So we will have a center, and then we have one step to the left or to the right. So we would have x of t plus a time step. And then we have a step to the left, so which is t minus delta t. And then we have the center value, which is x of t divided by delta t, the step size, squared. So this is one of the standard ways to approximate the second derivative. And this runs with a truncation error, which goes like delta t squared. Have you guys seen this formula before? So this is just a kind of working horse in essentially the solution of all differential equations. And then we have another famous formula for the first derivative, dx dt, which we approximate with x of t plus delta t minus x of t divided by delta t. This is probably something you have heard under the name of a famous mathematician. Anyone remembers what this is normally called? I think he was from Germany, and the name begins with E. Euler's. This is just the root for Euler's method. And it's normally called Euler's forward formula because you're moving one step ahead. So this is the way you get these expressions, if you're not familiar with that, is actually to take Taylor expansions around x plus delta, no, t plus delta t and t minus delta t, and then combine the expressions either by subtracting or adding. And then you can get this formula for the first derivative, second derivative, etc. So these are the standard kind of equations which are used in solutions of numerical solution of differential equations. That's the right way. So what I'm going to do now is to bring together this term here with one of these, and this term with one of these, so I can actually rewrite these terms. So I'm going simply to define. And now I have a delta x of t plus delta t, which is now given by x of t plus delta t minus x of t. And then I have my delta x of t, which is simply x of t minus x of t minus delta t. Then I can rewrite Newton's equation in terms of these new definitions. So Newton's equation then becomes simply equal to m. I have this delta t squared, and then this is multiplied with delta x of t plus delta t. I have another term which goes like minus m divided by delta t squared times this delta x of t. And then I have plus mu times delta x of t plus delta t divided by delta t. And this is equal to this force which is acting on the system. Then I multiply away delta t on both delta t squared on both sides. And then I can rewrite this in a very compact way. And I get the following. I get a delta x of t plus delta t, which is then equal to this minus. And now I'm going to just introduce the gradient again. So I'm going to rewrite this as a gradient, g, like that. So there's going to be a minus g here. And this is going to have the following terms: delta t squared divided by m plus mu of delta t plus, and then there's a new term here which goes like m divided by m plus mu delta t times delta x of t. And then I'm going to redefine the constants, and then you will recognize these as this term here is something I'm going to relabel as the learning rate, eta, because I have that in front of a gradient. And this term here is a term which I'm just going to call for delta. Now, if you look at this value of delta, so this is used as a way to motivate the equations which are coming now. If you use it, look at this value of delta. So let's just pause a little bit so people have time to write it down. If we do that, so if we take this lim of mu goes to 0 of delta, we see that that is going to be equal to 1. And if I take the lim of delta of mu goes to infinity, this is going to go to 0. So let's look back. So if I take the limit mu here, this one going to 0, then this parameter delta goes to 1. If I let mu go to infinity, then I will have 1 divided by infinity, and this is going to be equal to 0. So what we could say then is that this delta, we could define that to be a constant which lives between 0 and 1. Now we are going to rewrite the equations a little bit. So what we have now is delta x of t plus delta t is equal to minus this parameter eta times this derivative, the gradient, plus delta times this delta x of t. And now we do something else. So we let x of t go over to theta of n, our parameter. We let x of t plus delta t be theta of n plus 1. And then we let x of t minus delta t be our theta of n minus 1. So one step behind. And we have let this force, which we have, to be given by the gradient. So what do we have then? Well, what we have then, if we collect all these terms, we are going to get something which looks like the old iterative method, but it has a result which will also depend on a previous iteration. So that's why I like to call this memory, because you will often see people using that as a cheap numerical trick to actually have some information about previous steps, because in case your different iterations fluctuate a lot, when you add information from previous steps, then you can average out larger fluctuations in the values. So this is actually a way to reduce largely fluctuating values. It may not converge, but it normally gives a much better convergence. So the way you would implement this is now as follows. So if you take what we have here, and then we simply replace these x's with theta of n plus 1, as we had in the old Newton methods, we have a theta of n minus eta. And now I'm just going to write this as a g of theta of n. So the gradient evaluated there, plus this parameter delta of theta of n minus theta of n minus 1. So this is normally called the momentum parameter. And I like to call this more a memory, because this keeps track, it gives a weight to the previous values. And as I mentioned, this theta, now this delta is normally taken as a value between 0 and 1. So this obviously introduces a new parameter in your evaluations. So you're going to see tons of parameters which are being introduced in the calculations gradually as we move on. But this is actually gradient descent with momentum, where you're now giving a weight to a previous value. So the algorithm is very simple to set up. So, and this is what you would have to plug in project 1. So you would fix the initial guess. Guess for theta 0. You would fix the initial value for eta 0. And then you would also fix this momentum value. So this becomes just a parameter you need to play around with. And then we are going to initialize a vector. Initialize a vector v. V0 here. So the way we're going to do that is the algorithm is going to run while stopping criterion not met. Criterion not met. Then we are going to calculate this v. So that's v of n. So this is not a minus sign. It's as a v, which is being updated, equal to delta multiplied with theta of n minus the previous value. So we need to keep track of the previous value. Minus eta of g times theta of n. So we need to calculate the gradient. And then the next step is us updating theta of n plus 1, which is equal to theta of n plus this v of n. And then we have end while. So that's gradient descent with memory / momentum, where we actually give a weight to a previous value. So sometimes you will see these equations in another disguise, where you actually just multiply the previous value with a parameter, and you just leave the value theta at n unchanged. But this is essentially the basic philosophy behind gradient descent with momentum. Any questions? So it's pretty straightforward, as you can see. As I mentioned also, you will encounter this in another disguise, where you could even find this term here, just written as a theta of n plus some parameter alpha multiplied with theta of n minus 1. So this has been a trick, a kind of ad hoc trick where you just give a weight to a previous iteration. And the hope then is that this weighting softens eventual fluctuations from one step to the next step. Because when you move along a gradient, you can suddenly hit a spike. So the hope then is that you dampen a little bit the spikes, which you can see when you're moving down towards the optimum value. So let's move on and take a closer look at the code then. So there is a code example, a pretty simple one. And this is this function, which I hope you don't get offended here. So in this case, I just implement a standard gradient descent, and I call eta for the step size. And you see now I have take the gradient, and then and in this specific case, the gradient is now just 2 times x. And if I can use this function here, so you see I have a step size of 0.1. I do 30 iterations. And then what I'm doing is to plot obviously the function, but I write out the derivatives as well, or the function itself. So you see now that when I do 30 iterations, so my ideal point is here at 0. And what I've done here is simply to plot the values, and you can see now how the gradients are actually putting this along the function I want to evaluate. So this is actually a very useful exercise if you want to visualize your gradients when you're doing this kind of gradient stepping. Clearly, when you have many variables, it becomes difficult to visualize. But what you see now is that I needed, with that step size, I needed something like 30 iterations, and my function is not exactly equal to 0. It's almost 0. If I were to print more values, it wouldn't be exactly 0. But the point is that you see I'm using 30 iterations. The next function is actually implementing this one. So you have a new change, which is this v value, step size times gradient, plus momentum times change. So my change is actually being calculated here. So I have the new change, which is just the solution minus new change. And if I do that, so this is just implementing that method. If I do that, you will see now that, let me see now, where did it go? Yeah, you can see now that in my case here, if I insist on 30 iterations, so if we scroll back to the previous case, you will see now that after 30 iterations here, I have 10 to the minus 4. With momentum here, after roughly 17, 18 iterations, actually here, 14 iterations, I have the same result as I had in the previous case. And if I insist on 30 iterations, actually I'm getting a result which is as close to 0 as I could get with this precision. So roughly, when you look at these numbers here, I need only something like 14 iterations to reach the same value at that precision as I used with gradient descent without momentum. And you will see that when you're plugging that into your codes, a very simple change of your algorithm, where you simply add this parameter, momentum, and then keep track of a previous value. This can actually speed up a standard gradient descent. Okay, so this is something which you will have to implement. So what we are going to do now is to move over to gradient descent, stochastic gradient descent. So there are several reasons for using that. In project 1, you may ask yourself, why do we include that? Because we have much simpler functions. So the whole reason now is that we are preparing for using these gradient methods towards neural networks and deep learning methods, where you have tons of parameters to fit. So a stochastic gradient descent, and we are going to look at the details here, gives a efficient update of weights more frequently using a single or small batch. So what we are doing is actually to collect a smaller data set when we calculate gradients and derivatives. So let me quickly give a kind of motivation for that by looking at the Jupyter, at the whiteboard again. So think of you having a function which has a form like this. And this is just a one-dimensional function, but still it's quite difficult to actually find the global minimum. So ideally, we would like to be here of theta. Now, if I start my gradient descent here, for instance, so typically you would choose a given value. Then after some few steps, I would be stuck here and the program would stop and it would simply tell me that now we have found the optimal value. Now, in this specific case, I'm also using only, when I do a gradient descent, I'm actually using the full data set which I have. But you know that the gradient descent is very sensitive to where you start. So that's one drawback with the gradient descent. And at the same time, when I'm doing this, I'm actually calculating my gradients with the whole data set which I have. So which is also something which is CPU consuming. Now, the idea with the stochastic gradient descent is actually to pick a smaller data set and place yourself randomly again and again in different points. So you would explore this minimum, but then you could again start here with a limited data set and explore this minimum. And then at the end, when you move on and on and on, the idea is then to calculate an average value for the gradient. And hopefully then by this kind of placing yourself, you will at random with different starting values and with different data sets. The hope then is that this will bring you closer to the true minimum. You may not reach that, but it is an approach which, when you have a big data set, functions much better. And I will show you the different arguments for how you can reach the true global minimum. But let's go back to the Jupyter notebook and look at some of the arguments and then try to translate that into codes and see whether we get something better. Now, what you're going to see for low dimensional functions like this one is that stochastic gradient descent will not have the same precision. You will see that from the examples. The plain stochastic gradient descent. So the idea here is that it hopefully avoids local minima. Memory usage, it requires less memory compared to computing gradients for the entire data set, which we discussed before the break. So in gradient descent, we compute the cost function and its gradient for all data points we have. So in many of these large scale applications, this is one of these challenges on images. The training data can have an order of millions of examples or more. Then it's actually wasteful to compute the full cost function over the entire training set in order to perform only a single parameter update. And a very common approach then to addressing this channel is to compute the gradient over batches of the training data. So there are some pros and cons here. So it's faster than gradient descent because it uses only one training example per iteration, whereas gradient descent requires the entire data set. The speed advantage becomes more significant as the size of the data increases. Convergence, gradient descent has a more predictable convergence because it uses the average gradient of the entire data set. Stochastic gradient descent's convergence can be more erratic due to its random sampling. Yeah? Could you say again?
Is it possible to change the size of the batches?
Yes. Yeah. So what you will do in project one is to play around with different batch sizes.
But in iterations as well, like in training.
You can do that during the training as well. You can do that. So that's pretty common to actually have some conditions which tells you that now you're not doing too well. I need to increase the batches and also the number of epochs. We are coming back to that. So we are going to introduce new parameters. So when we said momentum, that's an additional parameter to the learning rate. And then if you're using a hyperparameter like in region lasso, you have an additional parameter. And now you're going to see that there will be more and more parameters being sneaked in. So stochastic gradient descent has normally a faster convergence rate due to the use of single training. But then, as you will see now, in general, stochastic gradient descent is less accurate than gradient descent as it calculates the gradient on single examples, which may not accurately represent the overall data set. The gradient descent is more accurate, but the advantage here is actually when you move into larger data sets. So the typical way, so let's just look a little bit closer what we are going to do now. So we have a cost function, which now is defined by the whole data set, as we have done before. So this C of I could now be the mean squared error, but we just leave it undefined here. Then what we are doing when we did the standard approach is actually that we then would run and calculate all the gradients of these functions. That's what we have been doing till now. The stochasticity randomness is introduced by only taking the gradient on a subset of the data. And these are normally called mini batches. So you split your data into what's called batches. So if you have n data points and the size of each mini batch is m, then you have in total n divided by m mini batches. So a simple example is you having 10 data points, and you choose m equal to 5 mini batches. That means that each mini batch contains 2 data points. So for each mini batch, you would then calculate the gradient. Now, every time you do this, you place yourself randomly in the data set, and then you calculate the gradient starting from that point. So let's look at how this can be applied. So ideally then, what you have is a sum of all these batches, and this is the way you would calculate the gradient as an average of all these batches. So a gradient step descent now looks like this, where you have a single value j for one of these, this is after iteration j, and you would have a learning rate which can be updated, and then you will simply have the i's in the element of the batch. Now, the simplest code you have is a code like this one. So you have 100 points, you define the number of batches, and then you normally try to set this up so that you can divide the number of batches by the number of data by number of batches, and you get an integer number. Now, then there is something which is called epochs, and epochs is another parameter. So that means that what you would do now is that you would loop over the epochs, and for every epoch, you calculate a set of mini batches. You find randomly the points where you start, you compute the gradients, and then you compute new suggestions for the parameters, and then you keep updating. So I'm going to show you a simple problem here after we've gone through this one. So this is an example of a code with a number of mini batches, which can vary. So we have the standard equations, which we have seen before for ordinary least squares. So we are simply setting up the design matrix, and then we invert x transpose times x. This is the inversion which we do. We can do our own gradient descent without stochasticity. But let's now look at how we can do this for stochastic gradient descent. So we define number of epochs, so this becomes a parameter. What we have here is a number of batches, and this is the number of size of each batch, and then the number of mini batches. Now, this T here is something I have to say something about quickly. This is a way, what we normally call a cheap and poor scientist way of updating the learning rate. So you can have a linear dependence, and let me just have that as a small intermezzo before we go back to the code. So when you're updating the learning rate, and this is one of the reasons why we are looking at more advanced methods, you can do this in the cheapest possible way, and you could just think of the following. So let's just do that as a small step before we move on. So let's so the cheap ways to update the learning rate. Eta. So clearly 1 is eta constant. And this is what we have done till now. So no change. Then another one which you can encounter in the literature is actually an exponential decay. So then the learning rate is now a function of the number of iterations, and this is multiplied. So we have the initial learning rate, the one we start with, and then this is decaying now as a function of minus k, the iterations we are doing, multiplied by a constant, gamma of tau. So this constant gamma of tau is something which we have to preset in the beginning, and this is sometimes just set up as n0 divided by 100 or similar. So what you see in this case is that for every iteration, the learning rate becomes smaller and smaller. So if I start with 10 to the minus 1, I may, after 100 iterations, I may have gotten to 10 to the minus 3, as an example. So this is one of these, what I call cheap for scientists approach of doing it. We have other ways of doing that, which you will encounter in the literature. And one of these is one of the methods which we have put in the slides, linear. So where you would now have an eta of k, which is given by some 1 minus some constant alpha is a parameter, plus some alpha times some parameter, again, gamma of tau. And this gamma of tau needs to be set. And this is again often given as eta 0 divided by some constant, say 100. And alpha is a parameter which is typically set to live between 0 and 1. What you see now is that you have two parameters. You have alpha and you have gamma. So these are parameters. So your results will then depend on the parameters you choose. So you see this kind of what I call cheap way of doing it. It's going to scale the learning rate and make it smaller. So you would typically run calculations with a grid of starting values. So they could be 10 to the minus 5, 10 to the minus 4, or 10 to the minus 1. And for each starting value, eta 0, you reduce the value. But this has no knowledge about the gradients. It has no knowledge about the system. It's just a simple ad hoc way to shrink the learning rate. So the code which you are going to see first here is actually doing that. And it's not very elegant, but it's one of the ways you can do that cheaply without calling ADA-grad or root mean square propagation or some of these other methods. So here I have a kind of learning rate which is given by what I call a learning schedule, where I have an initial value, T0, which is put to 5, and then for every iteration, it shrinks the value, and it has the new value of the iteration plus this number, which is equal to 50. So these become parameters, and it's not so satisfactory. That's one way to shrink it. Now, the important thing is actually what is happening here. So now I'm having a loop over the epochs, and for every epoch, you can think of that, every one of these, as an experiment. And for every one of these, I'm going to now have a loop over the batches. The loop over batches does not need to include all of them. But what you see now is that I am finding a random index in my data set. So I place myself randomly. I have a reduced number of points, which is then given by this random index till random index plus m. So m is the size of my batch. So in that specific case, I have now chosen m to be equal to 5. So I'm calculating the gradient for only 5 points instead of calculating the gradient for 100. So if you go back to these discussions we had before the break, you see now that my calculations of the matrix multiplications is going to be much smaller. Now, gradient descent, the stochastic variant, is a little bit more tricky when it comes to pre-calculate things, because now we are placing ourselves randomly. So in the previous case, we could pre-calculate x transpose times x and x transpose times y and just store them and then multiply with the vector. Now we have to be a little bit more careful. But you see also that if you go back down here, you see now that I'm having this way to update the learning rate. So this is this cheap way, which is given by this function. But I could actually kept it constant. But now my gradient is calculated over only the data set M. And again, here you see now I have my x of I transposed times x of I times theta minus y of I. And then I keep going here again and again. And then I repeat the experiments. So you can think of this as an average gradient. And if I run the code here, what you will see now is that my own inversion and my own gradient descent, the brute force one, is giving exactly the same values. But now my stochastic gradient descent gives something which is less accurate. So this is something which you will often see in numerical computations. So how many of you are familiar with Monte Carlo integration? Okay. If you compare Monte Carlo integration, suppose you have a two-dimensional integral and you compare that with the Gaussian quadrature or the trapezoidal rule, which method wins? No. When you have a low-dimensional integral, it's actually the opposite. It's when you have a low-dimensional one, you can actually find that the error shrinks when you increase the number of integration points. So the trapezoidal rule will always beat Monte Carlo. But then there is a brink when Monte Carlo methods take over, because the error in Monte Carlo methods goes like 1 over the square root of number of attempts. So if I calculate a 10-dimensional integral and compare that with trapezoidal rule, the Monte Carlo method will beat the trapezoidal rule again and again. So what you're seeing now is that we are looking at a simple case, a very simple case. And in a simple case, we can actually run the full gradient calculation. And that will give a better result than the stochastic one. But when the dimensionality is going to increase, there is no way you can use the simpler methods because the dimensionality is too big. You won't be able to store the matrices. You will have huge memory requirements and so on and so on. And this is where the stochastic gradient descent kicks in. So just think of this comparison between Monte Carlo methods and traditional integration methods. When you reach a certain dimensionality, the traditional methods, which is you refining the step size or the integration points again and again, they cannot beat a method which has a more global stochastical error. Okay, so it is a parallel to this. So the more degrees of freedom you have, the more difficult it becomes for the traditional methods. So in essence, if you look at these codes, this is what we want you to implement. Now, there is a big issue because what we have done here is that we have used what's called replacement. So it may not be fully, I mean, in Norwegian, this would be med tilbakelegging. So if you're thinking of a stochastic event, you can bring it back again and then ask what is the probability. So there's actually a big debate in the literature whether this replacement is the way you should do it or not. So keep in mind that what you're seeing now is very much like almost an ad hoc recipe. And the field is very much tainted by this trial and error. What is functioning, what is not functioning. And then often a more deeper theoretical understanding comes a little bit later. This is much the way science moves. Like when physicists introduced quantization, it took some time before the mathematics of Hilbert spaces came into a proper mathematical foundation. So, and the same with the mathematics of deep learning. That is a brand new field in mathematics where people are trying to really sort out what is happening here mathematically. Why does it behave like it does? And you will actually often see statements in the literature that we tried stochastic gradient descent and we tried gradient descent, gradient descent work better, although we expect the stochastic gradient descent to work better, but we don't know why. So these are statements which you can still find in the literature. So it's a field where trial and error still plays a very important role. So there are lots of discussions, and if you click on this link, you can actually follow some of the discussions here. And when you now look at if you go into the slides, I put in some additional material about the theoretical speed and convex optimization. So take a look at this material. I will not cover everything in the slides, but I added some additional material on speed and tests which have been done, depending on the type of functions which are dealing with. And there are lots of papers in the literature where people have tried different options and try to understand what's happening. So I'm not going to go through this, but the kind of deep wisdom which you have is that when you go to deep neural networks, which we are going to cover in project 2, the full batch gradient descent is so slow that it is normally never used. So the stochastic gradient descent is actually the standard approach, where you actually place yourself randomly in a data set and then compute gradients with lower data. And then you repeat this again and again over a set of batches of data, mini batches. And then you average out. And the hope then is that you get a better result than you would get by computing the big gradient on the whole data set. Because in many cases, you can actually not store the whole gradient, especially if you have millions of parameters. There's no way you can do it. And that's where stochastic gradient descent comes into play, especially with neural networks, where you would have to keep track of the values from the previous layers all the time. And that becomes extremely time consuming from a memory management point of view. Now, the methods which I was hoping to say something about is actually the adaptive methods with AdaGrad. What I put in the lectures here, so I will have to do this next time, but feel free to take a look at them. And these are some of the very popular methods, and you would find code examples, the description of the algorithms here, root mean square propagation, and then what is a kind of golden standard, which is the root mean square propagation. And the algorithm is actually described here. And the codes which you have in the Jupyter notebook for this week actually do this. So next week, I was hoping to cover more, but I'm pretty slow. So I'm going to discuss them in the first lecture before we then move into resampling methods, which we'll also need for project number 1. But next week, I will try to catch up and discuss these 3 popular methods. But for the exercises this week and also for project, what we have till now with the stochastic gradient descent with momentum, you can add momentum to stochastic gradient descent as well. And this is normally done. These are things which you can play around with. And when you're going to include your own stochastic gradient descent, in the beginning, it can be a little bit frustrating because you have to play around with parameters like the number of batches, the number of epochs. And in your case, you're going to have the exact answer. And you will not be too happy with stochastic gradient descent because you have to tweak the parameters to get to the exact answer. But this is the kind of consolation you can think of then in project 1, is that now you're applying these gradient methods to baby cases. It's only when you go to multidimensional beasts that these methods come to their really true, efficiency. So for low dimensional cases like the one we are looking at, the standard gradient descent and also disappointingly, ordinary squares is going to beat the other methods. Okay, guys. I hope this was a kind of first introduction, and next week we try to wrap it up. But feel free to look at the slides and the codes. Okay, I'm going to stop here.